right, hello everyone. Welcome to tonight's presentation. My name is Amanda. I'm one of our education coordinators here. I'm really excited to welcome you. We have a wonderful presentation from the absolutely amazing, as many of you who have been return visitors will know. We have Dave McDonald here tonight to talk about the gravity of it all. We're going to have some fun little demonstrations. Don't worry, we will not make you do laundry. Okay. Dave has been with us since 2002. He was our education director for quite a while and is now for 10 years and now has been with us as one of our senior educators. We are so lucky to have him. I know that you're going to enjoy his presentation tonight, so without further ado, I'm going to pass it off to Dave McDonald. Thank you.
Good to see everybody. Thank you so much for coming tonight. A little chilly out there, so it's nice to be in here. But between our little break between our presentation here and the Planetarium Theater show, pop outside for 10, 15 minutes because we have some astronomers here with the New Hampshire Astronomical Society, and they have some decent instruments and such. And something I'll talk about a little more in the theater is this is the month of opposition of Jupiter. This is the best month in like 10 years, to see Jupiter, and I'm sure they'll be looking at it outside. So,
what's the brightest star in the sky right now?
What's that?
The brightest star in the sky right now?
Venus.
Venus.
Venus. Yeah, Venus is about 6.5 times brighter than Jupiter is. What does this want to do? Give subtitles a try? No. Go away. So, this is Superstellar Friday, and it is December 6, 2024. And we're going to go for a little bit of a ride. So, I hope, one thing that we're taught as presenters is equations are death to an audience. Not for me, and because you're here, I trust not for you. Nothing like a good old equation to wake people up, right? Okay? I like that that was an enthusiastic shaking of the head. Are you like a math major or something? Good. What grade are you in? Eighth is a good grade. I was in 8th grade 3 times. Kidding. So, what do you think? Agreed? So our solar system has its problems, and it's had its problems. And for thousands of years, we knew about Mercury, Venus, Earth, Mars, Jupiter, and Saturn. You know, the standard planets have been known for thousands of years. But the mystery was, how does it work? And so, astronomers of the past had some different ideas about these things. This guy was pretty smart. Aristarchus of Samos, around 310 to 230 BC, was a Greek astronomer who first proposed a heliocentric model of the universe in which the sun, and not Earth, oh dear, I put the particles up there, not Earth, was at the center. It just didn't gain traction. I was going to say it just didn't gain attraction, but I think I overused that one. So anyway, pretty amazing. Does anybody know what heliocentric means? That's an important word. Yes, sir.
The sun is at the center of the universe instead of Earth.
The sun is at the center of our solar system. Helio is sun, and centric, center. And helio comes from helium, and you know this, you've heard of the element helium. I mean, who hasn't played with helium balloons, right? That helium was discovered on the sun before it was discovered on Earth. It's the only element that was discovered on another body first before it was discovered here on Earth. So anyway, yeah, so the sun is at the center. And this guy, way back, let's just say 250 years before Christ, had this idea, but it just didn't catch on. Then Aristotle, everybody's heard of, was the geocentric, and geocentric means what? Earth, geography, geocentric. The Earth is at the center of the solar system. And he nested spheres of different sorts to try to figure this out. And then Ptolemy, who followed Aristotle's ideas, but with some adjusting of the ideas, and he was really interested in the mathematical modeling of how things worked and the motion of the planets. That was the big enigma. It seemed as though the stars stayed put, you know, the constellations that people made up, civilizations made up, they didn't seem to change. But the planets, that was the problem. So many followed Ptolemy and tried to solve the problem of the planets. I'm going to show you what the problem of the planets is in just a moment. And they made various types of tries to make it work with what's called epicycles. And I'll show you what that is about as well. So here's the problem. This is an example of Mars. So Mars generally moves from west to east. That's the normal motion of the planets and the moon across the sky from night to night, month to month, is west to east, not east to west. Things rise in the east and set in the west because Earth rotates, but the motion of the planets is counterclockwise around the sun if you look at it from above. Okay? So the standard normal motion of planets is from west to east, like you see here. Then something happens. And Mars, the other planets do it as well. Mars is the bigger example because it does it more dramatically because it's closer to us. It turns around and it goes back and it moves from east to west for a period of time, stops, and then continues its normal motion from west to east. This motion here, when going from east to west, is called retrograde motion, retro, opposite, and that's the path of Mars. This is a problem. And other planets, Jupiter and Saturn, did this as well, not to the same extent, and that was a big problem. So, interestingly enough, mark this down on your calendars, you'll remember it, this is happening tomorrow night. Tomorrow, this is happening. Mars is going to stop and go the other way. Right now, tonight, and for the past months, Mars has been moving this way here, and then tomorrow it's going to stop and come back this way. And I wish we did this a week ago so you could go out and watch and see, oh yeah, there's Mars, it's moving against the background of the stars. If you go out from night to night, you can see it moves a little bit from the stars, from west to east. And then tomorrow it's like, well, the 6th to the 7th, it's like it didn't move. And then all of a sudden, oh my gosh, on the 8th, it's going the other way. And it's really kind of neat to watch it and to note it, and then to try to note, and I don't have the date of when it turns around, goes the other way, but it's not like months, maybe a month. So it comes around, it goes the other way. But this is the problem. Nobody could explain this. So Ptolemy came up with this idea. Again, Earth is at the center. So we have Earth here, and Mercury goes around Earth. The sun has to be somewhere, obviously. But for things to work the way we saw them on Earth, it's like Mercury had to have its little orbit as it orbited. That's an epicycle. And then Venus had to have its little orbit as it orbited around Earth. And then the sun went around Earth. And then Mars had its little epicycle, and Jupiter and Saturn, and then the sphere of fixed stars, because it seemed as though the stars stayed put and didn't go anywhere. Question? All right. So, from dead center of this circle, Earth is here in what's called the equant, which is a similar distance from the center. And we have the planets going around, and they tried to explain this loop-the-loop motion that was observed, because clearly it was happening, but where are the planets and how are they moving to make that happen? So Copernicus shows up, and Copernicus wrote De Revolutionibus, if that's how you say it, in 1530, and he put the sun at the center. So remember that Aristarchus, many moons ago, had the sun at the center, but it just didn't catch on. So Copernicus now has the sun at the center here, no drawings not to scale, with the planets. And so in terms of describing what's happening, it wasn't a whole lot more accurate. It's, you know, putting this thing here in uniform circular motion. He thought everything was perfectly circles, and these small epicycles were still needed. But it was a total change in thinking, because it's starting to gain some traction here. There are some people who are like, I don't know, but they're willing to give it a thought. And one big thing in science, in observing astronomy, at that time, astrology was a science. It changed. That's another story. But anyway, science, observing is really important, and thinking, being willing to think outside the box is an important aspect of science. So this guy, this Danish astronomer, Tycho Brahe, or Tycho Brahe, shows up, a Danish nobleman, and on November 11th, 1572, a new star shows up in the constellation of Cassiopeia, or Cassiopeia, or Cassiopeia, however you want to say it. The Queen of Ethiopia, the constellation that kind of looks like an M or a W or an E or a 3 or a capital Greek sigma in the sky. Easy enough to find. I'll show you how to find that tonight and such. And so something new happened, because the predominant thought was the heavens don't change. We know the planets do strange things, but the stars are unchangeable. But he was really good at taking precise measurements of where the stars were and where the planets are. And he basically showed, no, the heavens do change. We have a new star. Turns out, again, to be a supernova in the constellation of Cassiopeia. And so he comes up with a new, different kind of geocentric model. Smart guy. So here's Earth. And things go around Earth here and here, and it's kind of like weird to look at it and see how these other planets go around Earth, but that's kind of, again, a general concept of what he came up with, a little on the different side. So Tycho Brahe, he dies in 1601, and his accurate tables, because they were very accurate, were given to Kepler. And this is a debate. Some people agree, yeah, Tycho's like here, because they were colleagues, astronomical colleagues, and Tycho's like, here's my data, do something with it. I'm not long for this Earth. Others are like, Kepler stole it. So anyway, little debate on how Kepler actually got the info, but he got the information. He got some really good data. And so he developed his laws of planetary motion. 3 basic laws that he became famous for. The first law being that the planets orbit the sun, and the sun's not at the center. It's not a circle, it's an ellipse. And the sun is at one focus of the ellipse. Law number 1. And law number 2, and I'm going to show you another slide with the same info, has to do with, well, how fast does this work, and it seems as though planets move faster when they're closer to the sun, and they move more slowly when they're further away from the sun. What causes that? And then the third law relates the period, which is the time it takes a planet to go around the sun, with the cube of its semi-major axis. I'll show you what that is in a little bit, or the average distance from the sun. So Kepler, he was a believer in the Copernican theory. He believed, yes, I think the sun is at the center. And he played with these 5 regular solids, tetrahedron and a cube and other figures I can't pronounce, and developed what's called the Rudolphine tables, which is more data, more information about where things appear in the sky. And he said, you know, Mars, in 1606 he's saying, Mars has an elliptical orbit, and that's part of what we see happening. That's part of the solution to the problem. And these planets move at different speeds. They're not always going the same speed around the sun. And so Astronomia Nova, the new astronomy, was born. So his laws of planetary motion: the orbits of planets are ellipses with the sun at one focus. A line from a planet to the sun sweeps out equal areas in equal periods of time. I'll show you that in a little bit. And then a planet's orbital period squared, the time it takes to go around the sun, take that period and square it, is equal to or proportional to its average distance from the sun, or its semi-major axis, which is taking the long axis and cutting it in half, cubed. So capital P is the period squared. A is the distance, the average distance, or the semi-major axis squared. P is measured in years, and A is measured in AUs, astronomical units, or the distance from sun to earth is 1 AU by definition, 1 astronomical unit, roughly 93 million miles. Question? Okay? So, a little better diagram on part of it. So, again, the orbits are ellipses with the sun at one focus, not at the middle. It's actually fairly close to the middle-ish, but it's not in the center. And then here, this idea of equal areas and equal time. When a planet is closer to the sun, it moves more quickly. So in 6 months, it moves from here to here. In 6 months, on the other side, when the planet is further away from the sun, it moves from here to here. Not so far. But the area of this triangle here, which is roughly a triangle, one side is curved, and that side is more distinctively curved. But in any case, this area here is the same as this area here. And so that was a big find. And then the other one that I shared with you, that the square of the period is proportional to the square of the semi-major axis, which is this part. So here's your ellipse, here's the major axis, the semi-major axis is half of it. So he came up with those laws. So here's a little math. You can do this in your head, right? If Jupiter's average distance from the sun is 5.2 AU, what's the period of Jupiter's orbit around the sun? Okay, hands. So P squared, remember P is the time it takes to go around, and that's what we're looking for, is equal to the average distance from the sun cubed. So 5.2 cubed, you know this, right? 140.6, everybody knows that one. Take the square root of that to solve for A, and you get about 11.8 years, and typically we round it to 12 years. So 11.8 years. So that's how you can solve that. And one of my favorite planets is Pluto, so I have to have a Pluto question. Pluto orbits the sun with a period of 247.7 years. We typically round it to 248. What is the average distance from the sun? Oh, you need something to play with when you get home, so you think about that one. Enter now Sir Isaac Newton. Kepler was able to describe what happened. He's like, okay, this is what's happening. But he didn't know why it happened. Galileo, I'm not going to talk much about him apart from he discovered some neat things that got him in trouble with the church, and it wasn't all that many years ago that he got pardoned. But anyway, Galileo died the year that Newton was born, so they never crossed paths physically in this life. So in the year 1642, Galileo died, Newton is born. Newton was a thinker. He enjoyed a thought. He enjoyed a thought experiment. Moon, what makes the moon orbit Earth? The path is curved, and he's thinking it should just go off in a straight line, right? It's like a slingshot. You get the rock or the ball, whatever you're swinging around, and you let it go, it takes off. When you let it go, it goes off in a straight line. The thing keeping it in, around, as you swing it around, is the cord or the string. Well, there's nothing attached to the moon to hold it. What's holding the Earth, excuse me, what's holding the moon to be not flying off, and what's holding the moon to be going around Earth, and there's no string, there's no bungee cord, there's no rope.
Gravity.
I know that word. So, I'm not going to go through the details of this, but just to point out, because sometimes it helps to know, way back here in the 1500s, we have Michelangelo, Leonardo da Vinci, and the boys. Here, Tycho Brahe is on the scene with his very accurate observings. Kepler overlaps. Tycho dies before Kepler does, and somewhere along the line hands off his information to Kepler. So, and Tycho, by the way, hired Kepler. So that's one way they got to know each other, because they were hired. Kepler worked for Tycho. And then he comes up with laws 1 and 2, and then 10 years later, law 3. This is kind of during the time of Shakespeare. I kind of think that's interesting. And then, again, Galileo dies, Newton is born, and writes the Principia, which was an incredible work. Math, science. If you like math, it's a good one. So watch the bottom right. Einstein. Well, he doesn't really fit very nicely in that timeline, because he's down the road a piece. He was born in 1876 and he died in 1955. And in 1905, he had his greatest hits. And another time, I can talk about those if that's of interest to you. But back to Newton. Name that law. Can anyone name this law here? What's that illustrating? Newton's first law.
Force.
Law of, not force?
Inertia.
Inertia, yes. An object at rest tends to stay at rest unless acted upon by another force. An object in motion tends to keep that same motion unless acted upon by another force. Force! Here, force equals ma. F equals ma. Force equals mass times acceleration. Force. And then his third law is the law of
Reaction.
action and reaction. Right? So I'm not suggesting you try this at home or in any museum, but if you can get hold of a skateboard and a fire extinguisher, you can have some fun. You get on the skateboard and fire the fire extinguisher, and the exhaust, basically the frozen carbon dioxide, is going to go that way, and you on the skateboard are going to go that way. Action, reaction. And that's basically how rockets fly. All this thrust coming out of the nozzles of the engines, and then the opposite reaction is the rocket goes up. So this is the big math equation here. One of them. There's two big ones. This is one big one. F sub g, the force of gravity, is equal to capital G, which is a gravitational constant, 6.11 times 10 to the minus 31st kilogram meters over newtons per second squared. Got that? So basically, the simplicity of it, G is a constant. You have the mass of one object. You have the mass of another object. So, for example, the mass of Earth, the mass of the moon, and r is the distance between them. You can think of it as a radius. It kind of is. It's kind of the radius from Earth out to the center of the moon. It's kind of like the radius of the moon out to the center of Earth in that direction, but it goes beyond the surface. But we call it r in any case. So take mass 1 times mass 2 divided by r squared and multiply by that constant, and we get the force of gravity. Because, you see, Newton thought that objects attract each other. There was an experiment done by Henry Cavendish down in the caves. Very, very delicate, very, very accurate experiment away from any air motions, where he had very, very, very delicate jewel, I don't know, kind of like ball bearings, fulcrums, rotational points, with two decently massed steel balls. I'm not sure they were steel, but significant metal. And another apparatus, and the idea was if he got them close enough, again, there's no air motion involved, and if he got them close enough and moved one set by the other set, would the one he's moving cause the other one to move? Yes. And his conclusion, basically, again, very quick summary, you can look it up, Henry Cavendish, neat experiment. Objects attract each other. And that was basically his big thing about gravity, is objects attract each other. Like that. So he got thinking to himself, suppose I fire a cannon. And if I fire a cannonball, it's going to go so far and land on Earth. If I put more gunpowder in the cannon, it's going to go further and land on Earth further away. And he's wondering, can I put enough gunpowder in my cannon so that the cannonball never lands? And he thought about it, so he fires it, and he thought, yes, I could if I had the right cannon and I had the right gunpowder and I had the right cannonball. I think it could work. But what's going to keep that cannonball to going around Earth is the same thing he was thinking about the moon going around Earth: gravity. And then the thought is, well, suppose I gave it even more gunpowder. I could create an ellipse, I could create a parabola, I could create a hyperbola where it's not coming back. So, Newton versus Einstein. What is gravity? We have the apple falling on its head, we have dropping objects, we have now a new diagram for you here with Einstein is like this fabric of space-time where objects are warping that fabric of space-time. So that's kind of interesting. So in 1905 he had his greatest hits. But he came up with this thought: massive objects warp the fabric of space-time. Enter his theory of general relativity. You may say his new theory of gravity. So, there's an eclipse coming up in 1919. So 6 years earlier-ish, Einstein in 1913 writes a letter to astronomer G.E. Hale of Hale telescope fame, Palomar, 200-inch, looking for the bending of starlight during the solar eclipse. So this is a copy of his manuscript, which the letter he wrote. You see the diagram here is the sun, and there's a star back here that really is obscured by the sun. But Einstein's claiming the star that you should not be able to see because it's behind the sun, you're going to be able to see it. Because the sun is going to warp the fabric of space-time. The sun is going to warp that path, so it's going to look like the star's here, but it's really here. So, in 1919, the fateful day of the eclipse is coming, and on May 29th, Einstein was your basic, good, popular scientist. But on May 30th, he was world famous because this was proven to be true. General relativity now has proof. And this is just a better example. Earth, sun, here's the star. That you can't actually see it because it's behind the sun. But during the eclipse, when the sun is blocked, that star appears to be here because the sun is bending this fabric of space-time so that it appears the star is here. Proven. Done. General theory of relativity is so massive objects do warp the fabric of space-time. Okay? Ready for another equation? Escape velocity. How do we get away from someplace? Well, we take 2 times g, there's that g, 6.11 times 10 to the minus 31st, etc. Capital M is the mass of something like Earth. It's the mass of the main body, capital M like Earth. R is the radius of that object. You multiply 2 times that g, multiply it times the mass of the object, divided by the radius, and we know what the mass of Earth is, and such, in kilograms and such. We know the mass of the sun is something like 10 to the 30th kilograms. And we know r is the radius from the center out to the surface of the object. We take the square root of it. Just push the button on your calculator, square root. And now we know what the escape velocity. How fast do you have to go to get away from that object? For Earth, it's about 25,000 miles an hour. You want to get away from Earth? 25,000 miles an hour should do it. Around 5,400 miles an hour if you want to take off from the moon. The sun is over 1 million miles an hour if you landed on the sun. Oh, I know what you're thinking. Why would you land on the sun? You go at night. So, black holes is a remnant of a supernova that's more massive after it's puffed off its stuff. 3 solar masses. Nothing's going to stop its collapse. It's going to continue to collapse. Eventually, the gravitational force is so intense that even light cannot escape. And the remnant that's left over has become a black hole. Because, here's the formula. You just need an object that is massive enough, that is a small enough radius, right? So we want big mass, lots of mass, and we want a small r, we want a small radius, so something very massive in a very small space. And when we do the math, we just want the number to be greater than 3.00 times 10 to the 8th meters per second, or 186,282 miles per second, which is like going around the equator of Earth in 7.5 minutes. Sorry, take it back. Going around the equator of Earth 7.5 times in 1 second. Pretty fast. So if you get a number that's bigger than that one, it's a black hole. So you can figure out, you can make up your own stuff. How massive is your object? How small is the radius of it? Do the math. You can write a computer program. You can write a program on programmable calculators and just play with it and say, well, if I had this mass and if I had this small radius, I made myself a black hole. The math is really fairly straightforward. So, according to Einstein's theory, the collapsed object creates an extreme distortion of space. So, Einstein's theory of relativity now is taking Newton's idea of two objects attracting each other and saying, no, it doesn't work that way at all. It seems like it, and his formulas actually work pretty doggone good for normal stuff going at normal speeds. But it's really more like the fabric of space-time, and an object creates an indentation in that fabric of space-time, and a black hole basically creates a rip in the fabric of space-time, so something rolls in, it doesn't get out. So, let's play with some stuff. So we're going to move a table over out there somewhere. So you can, where do you think we're going to move this to? Where would you like?
Well, I'll turn the projector off for now.
So now we can put it back where it came from. Okay.
Can everyone see mostly okay? You're welcome to come on up a little bit closer if you can't quite see in the back.
We're going to do this one first.
Perfect, that's totally fine.
Okay. Things are rolling. Watch out where you're going. You have arrived. Okay. All right. So, feel free to gather, feel free to stand if you'd like. This is the fabric of space-time. It's spandex sheet. The best I could find at Joann Fabrics was 25% spandex. 50% or more is better, but you have to get what you want. So this is the fabric of space-time. Okay? So again, you're welcome to stand, you're welcome to come around, because the important piece is how much things are going to indent this. So here's a ping pong ball. How much did it indent? No, not only not much, it's like nothing. It's right there. So here you have that. So something smaller than the ping pong ball, like this size here, watch. Seems to like being over this way. I think the Home Depot bucket is not level. But anyway, you can see there is an indentation now, right? Mm-hmm. But this is smaller than this. Why does this make the indentation?
More massive.
It's more massive, right? It's more massive. You can say heavier, but that's only related to Earth. Mass doesn't change anywhere in the universe. Mass stays the same. Weight changes. So, there's that. We have a golf ball. Definitely is not level, but in any case. Small indentation there. Then let's take something that's larger, like this size. You see those reflexes? Thank you for noticing. How much of an indentation is going on there? A little bit. How does that indentation of this significantly larger object compare to this much smaller object? More indentation? Yes. Why? More mass, smaller radius. Bigger radius, less mass, not much of an indentation. So let's get something like this. What do you think this one's going to do? I know you don't know what its mass is, but what would you guess? Yeah, this is like nothing. I think it's lighter than a ping pong ball.
Not plastic.
Yeah. All right, next on our show. Let's compare these. You familiar with this? See that little sandbag? Whoa. Something much bigger, about the size of maybe a candlepin bowling ball. Okay, a little bit of an indentation compared to this. Which one's more? One, two. One, two. How's your eyesight?
Blue.
All right, so smaller. So what do you think about this one here?
It's gonna go really deep. It's for the sand.
It's the most massive of all the things. So now think about this. Suppose I get something even smaller, this size, and even smaller. This is the smallest thing of any reasonable mass I could find. There are smaller, these are just a sinker, but the smallest ones don't even do anything. But just picture this mass in that size, what would happen? It's going to go really deep. And then if I kept being able, like this is 6 pounds of weight, which is about 2.5 kilograms. If I could get that and then it's even smaller, and increase the weight or the mass, keep increasing the mass, keep decreasing the size, eventually, what could I be able to do? Keep increasing the mass, keep decreasing the size, what eventually would happen? Rip it. Black hole, yes. So, I don't know what fabric I can do that with realistic things, but it would be pretty impressive if I could like rip the fabric of space-time, show you. Once it goes in, see all these things can get out, but once it goes into a black hole, there's no way out.
Sharp piece of awesome, yeah.
Yeah?
Yeah, it's the densest of all metals on Earth, and it's if you get like a sharp enough.
What's the density compared to water?
I don't know the exact number, but I think it's like I know it's the densest.
Okay.
It's definitely far heavier.
Well, good. Interesting, was that helpful? Yes, no, yes?
Yes.
Okay, good. So, and you can do this at your home, you just need a Home Depot bucket, don't get any imitations, make sure it's a real certified Home Depot bucket. Piece of spandex, spongy cord, and get your own, various kinds of masses and try it and amaze your friends, experiment, and get some osmium and do that, or at least take a video for them. Okay, so there's that. Okay, back with the projector. And we'll just roll this out of the way. We're moving to the point where I need the jumpers. I don't need any cables, just the jumpers. So we'll just slide this way. All right, so we checked some stuff out. This is just an example of a black hole distorts the stuff behind it. More than a dozen black holes, more than that, have been discovered in our Milky Way galaxy. There's hundreds. Cygnus X1 was the first one that we discovered that gave evidence to, like, black holes seem to be real. And then we took a look at the center of our Milky Way galaxy in the constellation of Sagittarius. And right there where those arrows are pointing is where our central black hole is located. And you can see it kind of glowing, bursting there, because when stuff goes into a black hole, the black hole kind of burps and X-rays escape, which are detectable in the realm of the electromagnetic spectrum for X-rays. It's called Sag-A, or Sag-A star. Sag for Sagittarius, A first, star, it's a star. And this is one of my favorite illustrations. You can see the years going by from 1992 to 2000, 2006. So roughly 14 years of data there. And notice those are stars that are orbiting something, but we can't see the something. But we can figure the mass of the stars. We can certainly calculate what the orbital period is. And going back to Kepler and Newton, we can figure out, well, how massive is that thing? And it turns out that the massive of that thing, where the red X is like 3 million times the mass of our sun. And that's our black hole. They're real. That's an example of our actual photo of the X-ray jets coming out. M87, 55 million light years away. Between the constellation of Leo and Virgo is where you can find this. And who got to look at something special? Why, Katie Bowman. She was able to look at the first ever image of a black hole in the galaxy far, far away, M87. Why did they image M87 before imaging our own black hole? Because it's supermassive. 6 billion, with a B, 6 billion times the mass of our sun, where our black hole is a mere 3 million times the mass, maybe 4 million. And there it is, 2019, first ever image of a black hole. It's tough to see, touch something. It's tough to see something you can't see. But if you work at it long enough and you start to understand, if you get 3 people working together for a couple of years and some supercomputers, we can image our own Milky Way black hole. And there is that. A couple years ago, we got that. The Event Horizon, this is not about the telescope, but it's the Event Horizon telescope. It's 6 radio telescopes located in various places around the world, aimed at the center of our galaxy, with supercomputers and terabyte hard drives collecting data, and a lot of people sifting through the data, making sure the programming, the coding is right, and then in some instant, somewhere, on somebody's laptop, the image appears. It's like the computer's done, I'm done processing, here you go. Gravity waves. If 2 big things collide with each other, you get gravity waves. Einstein is now the leading theory of gravity. The curvature of space and time, mass, like I was showing you with the spandex sheet, mass tells the space how to curve. And the curvature tells the mass how to move. I could put a massive thing in the middle and like maybe taking that ping pong ball and kind of have it try to orbit, but the center was a little off center, so I didn't do that. But that's basically, that's the essence of Einstein's theory of relativity, is matter tells space how to curve, and the curvature of space tells matter how to move. Gravity wave, September 14, 2015, at the LIGO instruments, which are 2 instruments, Oregon and Louisiana, about 1,700 miles apart, and detected gravity waves. So the idea of gravity now is not 2 objects attracting each other, but rather this concept of gravity wells. And this is the same information, and it's just, I just have to push this to get it all to come up. Gravity waves. Oh, you got gravity wells? So here's an example of what a gravity well is like. I kind of illustrated it a little bit with the spandex sheet, but this kind of illustrates it, some of our planets that we have over here. We have Earth and our moon. We have Mars, less because Mars is roughly half the diameter of Earth. And then over here, we got Saturn and its rings, making a much larger, a much deeper, and then Jupiter making a really big gravity well to get into. And then Uranus and Neptune. And if I had time, I'd go into like some stars, some supermassive stars. Our star is kind of average it. But it's the things that are in space that are warping the fabric of space-time. No matter how big or how small the object is, it's not 2 objects attracting each other, but rather 2 objects creating gravity wells, and one gets caught in the other, in the movement of the other, and conservation of momentum. So, next, let's try some gravity wells. So, this is the idea, right? This is the formula. Here are the planets. I love this slide because it includes Pluto. And it has the escape velocities in kilometers per second. Okay? A kilometer is about 0.62 of a mile. So smaller than, bigger than half a mile, but 0.62, right? 62% of a mile is what a kilometer is. So you got Mercury, 4.3, Venus, more, Earth is a little more than Venus, Mars is a little less than half of Earth, Jupiter, the king, right, just about 60 kilometers per second, Saturn, 35, Uranus, 21, Neptune, 23, and Pluto, the smallest of all these, because Pluto is smaller than our moon at 1.3 kilometers per second. So the thing about that, it's kind of good if you landed on Pluto, easy to get away from it, but the problem is it's really tough to slow down to be able to land on it. That's a topic for another time. So, I need, these are gravity wells. Who wants to jump? Your hand was first. You can jump, so we can take turns. Because probably, we'll see, so you stand in there. Okay, can you jump out of it? Apparently you can. Stand in this one. Can you jump out of it? Yes. The strength in the legs for the jumping is equivalent to thrust of a rocket. If we had more time, we could do a jumping thing on the wall and just kind of see what everybody's thrust is worth. So next on our show, up in there, can you jump out? Yes. Okay, let me know if I need to catch you before you fall. Ready? Oh, not quite. Okay, but good try. So you got out of 3 things, so you can have a seat. So round of applause. What's your name? Adam. Round of applause. Okay, who thinks they can take it? Yeah, come on up. Okay, you got to get warmed up though, okay? So you just get in there. How about you can get out of that gravity well? Good. Get in that one. Hop out. Yes. Get in this one. Hop out. Yes. Looking good. Okay, here we go. Gravity wells are getting deeper. We are on, I think we're up to probably around Earth now. Oh, snagged also. You can go have a seat. Who wants to try this one? Okay, you want to come? So, for the sake of time, we'll just assume you can do those. Unless you want to just warm up, you can. Because doing this forward. You got to leave that in the ground. I'll hold it. These are, you know, pretty flimsy. So, and yeah, good. Yeah, you can try again. I'll try to hold it so it doesn't go up with your jump. Okay, you can escape Earth. All right, ready?
Not now.
Probably that's the plan for us, January 1st.
Okay, I think we took care of Jupiter there.
Oh, boy.
Okay. Now, to be honest with you, there are trash cans that are, you can sit down for that. And what's your name?
William.
William. Round of applause for William. There are trash cans that are bigger and deeper. I ran out of money. But you can envision, I mean, obviously, we would get to a point if maybe I should have spent another $30 if we got one, a deeper one. But eventually, whoever is doing it, eventually we're going to get to a trash can you can't jump out of. And it's the same thing with escape velocity. Eventually, you're going to get to something you can't escape out of. And once you get to something whose escape velocity is larger than the speed of light, if that's the speed limit on the universe, you're not getting out. So, questions?
How does Hawking radiation figure into all of that?
Hawking radiation is stuff that does, in theory, get out of a black hole. kind of leaks out. Anything else? So, thank you. I hope that was interesting, informative. You learned something you didn't know when you came in here. And hope you enjoyed a couple of equations and such.